Yeah, welcome back, everyone. This is Imperial Loben. Today we shall be exploring large vision models for mild disease retinal screening in Ugandan healthcare. Those are some of the keywords we shall be exploring throughout the presentation. So those are the contents of the presentation. We begin by exploring the background, the introduction, retinal crisis in Uganda. Why retina? Yeah, it's non-invasive and it allows the early detection really can prevent over 95% of the vision loss. Then we explore the critical gaps whereby one ophthalmologist really works on over 1 million people against the World Health Organization recommendation of one specialist per over 250,000 patients. Then we explore the limited access in rural areas of over 55% being rural areas facing limited access. Then we see the late diagnosis at late stages reaching out to 80%. Then we see the scale of the problems. We see diabetic retinopathy and hypertensive retinopathy are really dominating. So our solution, which is AI powered, really addresses all these. So we look at the recent trends, rated works, and literature review. With first generation, we see how one model is able to predict to handle one disease at a time. And in the second generation, we see the introduction of multi-label classification and the challenge being limited interoperability. And the third generation, how there is utilization of vision transformers plus knowledge graphs and incorporating medical reasoning, and the challenge being computational demands. And with our model, with our innovation, allowing for smart architecture ensemble, providing graph-based clinical reasoning and mobile optimized deployment, and allowing explainable AI for clinicians. And we look at explore the problem statements of which we see specialist shortage, economic constraints, geographical barriers, and so on. We go over exploring the clinical challenge of time constraints, disease diversity, diagnostic arteries, of which manual methods normally provide 70 to 85% accuracy. Then we explore the computational complexities, the class imbalance, the explainability, where there is need to establish clinical trust. Then we see mobile deployment, where we need deployment of below 50 MBs and limited and low and inference speeds. And the solution really addresses all these three dimensions. So we explored the research questions and objectives. So below there are the specific objectives, of which the among of them is to develop a robust disease classification system to establish explainable AI for clinical trust, amongst others. Then we explore the four profound key questions we are addressing. Multi-architecture performance can assemble models up to perform single architectures for multi-label retinal classification. Then we have clinical acceptance threshold. What accuracy and explainability levels are required for clinician trust and adoption amidst others, as you can see. So we'll look out at research contributions and outputs. We look at multi-architecture ensemble, mobile optimization, utilizing int8 quantization, and utilizing pruning and fine tuning the results, being able to achieve 87% size reduction of the model of the mobile optimized model. Then we see the performance gain, how we are able to utilize the F1 score versus single models, and how we are able to handle multi-level complexity of 45 diseases simultaneously, and how we are integrating explainable AI frameworks into our system, utilizing GradCamp for visual attention heat maps, SHARP for feature importance ranking, amongst others. Then we explore the methodology and system architecture, having like 3 layers: the data input, yeah, involving input processing and data input servicing. We see the second layer, model layer, encompassing feature extraction, graph extraction, and graph message passing, and also classifier. Then in our last layer, we see utilization of model weights, utilization of pre-trained model weights from Hugging Face in training the models, and utilizing the web interface on Hugging Face for model deployment. So we explore the nature of our data set, and we perform exploratory data analysis. We see over data sets consisting of over 3,000 high resolution retinal images, then divided the data set in the ratio of 70 to 20 to 10% for training, validation, and testing data, respectively. Then here we begin by visualizing the clinical knowledge graph, whereby we are able to view Uganda-specific diseases and the top 12 most connected diseases. So we continue with exploratory data analysis. We're able to view top 20 most common retinal diseases, and we see how diseases can can coexist via correlation matrix, and for the top 15 diseases. Continuing with exploratory data analysis, we're able to see correlation heat map of top 25 diseases and disease presence versus absence of top 10 diseases, amongst other visualizations. Then we explore outlier detection. We see how more than two different diseases can coexist or can be detected at the same time. Yeah, so we explore the model architecture and mathematical foundations of our models, of our 4 models. So we begin by graph clip architecture, and we explore the mathematical foundations. We see vision encoding, how it extracts spatial features from retinal images using ResNet 50 as the backbone, then utilizing vision encoding, text encoding, cross-mode attention, graph encoding, and feature fusion, and utilizing sigmoid function in the classification output. Then we continue with our second architectural model, which is vision language graph neural net. We look at its mathematical foundations or formulations, and we see how it utilizes multi-scale features, feature pyramid, language similarity, graph construction, and graph update, and global pooling via softmax, which utilizes attention, and using sigmoid as our classification output. Then we go to the third, which is scene graph transformation, and we see how it utilizes object detection, feature extraction, position encoding, transform updates, graph masking, graph pooling, and in the end utilizing graph classification output as sigmoid function. Then we look at our last model, which is vision graph neural net, which really combines vision transformer and punch level graph neural net. So it utilizes punch embeddings, edge weights, message passing, node updates, global pooling, and in the classification output, it utilizes sigmoid function. Continuing with results, we utilize K-fold cross-validation to ensure all data is being used during data training and validation. So we see visualization of the output of the second fold of cross-validation results. So continuing with variation, we see the F1 score heat map of all models versing all diseases sorted by average performance. Then we see we visualize best performing model per disease, and we see F1 score distribution per model. Continuing with visualization, we are able to visualize precision versus recall per model. And this is still visualization. Then we are able to contrast each model. We are able to contrast models depending on various metrics like best F1 score, precision recall, and accuracy. And we see a graph clip managed to come up as the best via best F1 score, which really allows better detection ability and reliability, which is vital for clinical usage and establishing trust within clinicians. So we look at mobile optimization performance analysis, utilizing quantization and pruning for model size reduction of up to 95.8%, and we are able to achieve a great inference speed of 65.8 frames per second, and inference time really reduced to over 15.20 milliseconds to have output. So we look at model selection and deployment. So graph creep model managed to be emerged out as the best and the selected one. And so looking at the deployment, we begin by model training. We train the model on our data set. Then we do containerization. We build the Docker image with NVIDIA CUDA support, and then in the third stage we do mobile model conversion using AI Edge Touch library to convert PyTouch format to TensorFlow Lite for mobile testing and deployment. Then tested and validated the optimized platform for Android and offered offline capability. Then deployed the app on the mobile Flutter app, and we deployed the containerized app on Hanging Face via Streamlit app. Then demonstration of visualization of the development products, the web user interface, and phone, and via the phone. So limitations, we explore requirement of clinical validation before independent use, then the need of connectivity for updates, then the limited generalizability across different populations, and the way how the model performance varies with different phones or cameras, and the need of retraining for evolving patterns. In conclusion, we are able to maintain accuracy of 80% rotation after optimization after successful mobile deployment success. And those are the future works of which we have already explored. So those are references, acknowledgements. Thanks for listening.